Um, so thanks, Ming, for inviting me and Chimiao, other organizers. This is fun. I'm sorry I haven't been able to participate in more, aside from a few talks yesterday, but that's life at the moment. So I'm going to tell you some work that goes back a few years with together with Steve Dodge and David Brun at Simon Fraser University, and Vivek Mishra, who's at IIT Madras in Zanzibar, and Tom Behrlein at Oak Ridge and their collaborators. We've been working on overdoped cuprates, so we're switching gears from nicolates to cuprates right now. Um, and there are a few papers that have come out recently, including this past year. So the cuprate phase diagram, everybody presumably knows. I'm going to focus on the overdoped side, um, where, sorry, I forgot to label the axes again, but I think you know what they are. Doping versus temperature versus doping. The overdoped side was supposed to be a simple limit for a long time in the sense that we believed that interactions were weakening away from the Mott insulator at half filling, and therefore BCS theory and Landau theory in the normal state should become applicable. And there is some evidence to that effect. There's been a lot of work on this, so let me just show you a couple of things about how quasiparticles due to ARPEs. I think this is from ZX Shen's group um, and Yao He. In BISCO 2212, sharpen up as you overdope. Even in the normal state, you see well-defined quasiparticles. And at the same time, the gap that you measured from the pullback of the EDC as a function of doping decreases the gap ratio and becomes closer to what you might think would be a BCS weak coupling value like 4 or 5 for 2 delta over KTC. On the other hand, there's been a bit of controversy regarding this question raised to a large extent by Ivan Bozovic, who made a series of very finely spaced in oxygen concentration uh, LSCO films, epitaxially grown in Brookhaven. And you see here a plot of the superfluid density that he measured in Kelvin units versus doping and versus temperature. And there are several things to note here. This is on the left, the full data set, and then on the right, that's just the low doping, sorry, the high doping and low TC data set blown up. You can see, first of all, that there is a superfluid density that decreases at the same time that TC goes down on the overdoped side. And you can see that the temperature dependence of the superfluid density, or the penetration depth, if you like, is quasi-linear in temperature. So here's the plot of TC versus rho S that Ivan produced in this Nature paper. So that's unexpected. BCS theory, we expect the superfluid density to scale as the carrier density, which would be a fairly weak dependence here, and instead it's scaling with TC. There are a couple of mechanisms which are pretty well known how this can happen. One of them is if you're in a regime where the phase fluctuations limit the critical temperature. This is Vic Emery and Steve Kivelson's idea from the 90s. So in the underdope regime, this theta max, this is the phase stiffness temperature, if you like, limits the TC in this picture. And the mean field transition temperature, which is decreasing as you overdope, again, presumably because the interactions are weakening, controls the critical temperature on the overdope side. So in this underdoped regime, you would get a nice proportionality, and that's seen in the famous Uemura plot, where you plot the transition temperature now versus something that's proportional to the superfluid density rather than the other way around. And you also see this backfolding effect the so-called boomerang effect on the overdoped side. There's another situation where rho s should be proportional to Tc, and that's an S-wave superconductor in the dirty limit. So if you take the ratio of rho s in the dirty limit to rho s in the clean limit, you get the mean free path divided by the coherence length. The penetration depth in a dirty system goes like C over L times the clean London penetration depth squared. Rho s goes like 1 over lambda squared, C naught goes like 1 over Tc, and sigma in the DC limit goes like the mean free path. So put those together and you get a proportionality between rho s and sigma DC Tc. And that's a well-known result, goes back, as far as I know, to Farrell and Schmidt back in the 60s. And it's been rediscovered a few times, including by Chris Holmes in this plot where he plotted the superfluid density versus sigma dc times Tc and found for cuprates initially, and later for a lot of other superconductors, including S-wave superconductors, that they all fell on a line. This is a log-log scale, so be careful. But nevertheless, there's a kind of a remarkable scaling over several decades, which I will come back to at the end of the talk. The problem with this argument applied to the cuprates is that they're not in the dirty limit, and of course, sigma dc is not really a constant. Okay, now there's another objection to the disorder explanation, which came from Ivan himself, and that is that the temperature dependence of the superfluid density was linear, as I said before. And it's known for a long time that if you have strong disorder in a D-wave superconductor, that the linear penetration depth as a function of temperature crosses over to something that looks like T squared. So a lot of people worked on this in the early 90s, and there's some kind of fit formula that you can use, which tells you something about the width of the impurity band in the system. And it didn't look that way. So Ivan said quite reasonably, this doesn't look like a disorder effect. But he didn't measure down to the lowest temperatures. And in addition, there's another feature which most people did not pick up on, although it's also been around for a long time, and that is that the crossover to the quadratic behavior depends a lot on the strength of the impurity scatter. So if you're talking about a zinc sitting in the copper oxygen plane, that's a very strong scatter, and it's probably close to the unitary limit. So it does induce this T squared behavior very rapidly. On the other hand, if you have a weak potential due perhaps to a dopant atom sitting away from the copper oxygen plane, the phase shift is much smaller. So you see that even for fixed scattering rate in this picture from Jim Sauls and collaborators back in '94, that you could see in the weak scattering limit, that what I labeled dopant limit, that it's pretty linear. So that's been known for a long time. So it's not clear that Ivan's argument necessarily works. So David Brun, Vivek Mishra, Steve Dodge, and I tried to take an approach where we're going to assume the simplest possible thing. We're going to assume that there is a Fermi liquid, that we have D-wave pairing, that we have pair breaking by dopant disorder, and that we take the doping dependence from the observed electronic structure in ARPA's experiments, changes of the Fermi surface. Put all that in and see if we can explain these experiments. And this is sort of in contrast to this trend that Igor Mazin commented on in this inverse Occam's razor paper, which I recommend to you if you haven't read it. Okay, so the equations are fairly simple and well known. It sometimes goes under the name of dirty D-wave theory. You have a BCS-like self-consistency equation, a gap equation. You assume a separable interaction with D-wave form. And then you have some equations for the disorder self-energy with the impurity phase shift built in here. And this is a average of the Green's function over the Fermi surface, essentially. Let me go back. Sorry, I didn't quite get to the superfluid density. This is the BCS expression for the superfluid density, this famous 3/2 function of Matsubara frequencies. So I'm not doing anything very fancy or new here, but if you do that and you go back and you can find a set of impurity parameters which allow you to fit the data very well. It gives you not only the scaling of TC with rho S naught, but it predicts that maybe at low temperatures there should be some curvature. It's hard to see because Ivan, for these samples, didn't measure low enough. There are definitely deviations at the very lowest TC samples, and I can come back to that and comment on that if anybody's interested. So, one thing that we wanted to do was to look at other materials. That was LSCO. We wanted to look at other materials which can be overdoped. And unfortunately, in the cuprates, there are only a couple of materials that you can take easily to very high doping and watch the superconducting dome disappear. And one of them is LSCO, and the other one is thallium-2201. So this was already known to be fairly clean, at least relative to LSCO, by the fact that you could see very nice quantum oscillations, which cannot be seen in LSCO as far as I know at the present time. Nobody's seen them. So the expectation was that this is significantly cleaner. So do we see a difference? Can we see that there's disorder playing a role here? And to make a rather long story short, when we did these calculations for both systems, again, taking the electronic structure from angle resolved photo emission in both cases, we found that you could fit the thallium data. It's much more dispersive than the LSCO data, but those are thallium crystals, which are notoriously hard to grow. So let's take this overall trend as being real. And then the message was that it's basically the same physics. We need to take the scattering rate due to dopant atoms in the thallium system to be about a factor of 3 smaller, factor of 3 cleaner. And that accounts for not only the superfluid density, which I've shown here, but also the optical properties of LSCO, the thermal conductivity and specific heat of thallium, which I don't really have time to show you right now. Then there was some criticism that these impurity parameters were kind of ad hoc. They were just fit parameters. So we worked with Tom Behrlein at Oak Ridge to calculate these impurity potentials from first principles. And these are oxygen vacancies and strontium dopants and thallium substituting for copper in the thallium system, or copper substituting for thallium, excuse me. And it works pretty much exactly the same. And that's in this paper down here in 22. I don't really have time to go into that story either. So now another issue that comes up in cuprates generally speaking, and in particular recently in the overdoped samples, is the question of whether or not there's inhomogeneity in the samples, whether the inhomogeneity is intrinsic, and in particular whether or not it's controlling the superfluid density on the overdoped side of the dome. So I'm just raising these questions here. I'm not providing a definitive answer. I think it's clear that many of these samples are inhomogeneous. You can see this in STM. This is a recent paper from, I think, John Tronquata and co-workers. This is an STM picture of a 30% doped LSCO sample. It's a mess. Okay, now some of that mess may be electronically induced disorder from point-like impurities, and some of it may be chemical structures, linear defects, dislocations, lots of garbage that can be in these samples as they're grown. We don't always know. Okay, and I can go into detail on that too if anybody is interested. They have a picture that in this paper that the transition to the normal state takes place as you overdope by the gradual accumulation of, or I should say the other way around, the gradual disappearance of superconducting islands, which then lead you to a lack of percolation finally and the end of superconductivity. So we wanted to investigate this question. And the nice thing is if you make the single assumption that yes, the uh, inhomogeneity that we're worried about in cuprate samples is coming from disorder, and that the massive disorder, the massive inhomogeneity that you see is probably due to the fact that the system, because it's close to the Mott insulating phase, is maybe close to a phase separation. And so these effects are all magnified in this strongly correlated system. We can simulate that with a Bogoliubov-de Gennes simulation where we put in some dopant atoms by hand. In this particular case, we took the impurity potential to be T, the hopping, which is a weak to intermediate strength potential, not a unitary scatterer for those who are interested. And we looked at two calculations. One is a Bogoliubov-de Gennes simulation, which takes into account self-consistently the suppression of the order parameter around each impurity and the interference of those effects. And the other is a disorder averaged SCTMA calculations. That's self-consistent T-matrix approximation. And all these equations that I showed you are based on the assumption of an effective medium approach where the disorder is averaged over. And so that's what I'm testing here. And the question we asked was, to what extent can this theory be trusted when you have an inhomogeneous system? And you see the result here, which is that you start with a clean system, you calculate the superfluid density in a progressively larger number of impurities, and eventually the two results for the disorder average theory and the simulation, they break ranks. But it doesn't happen until the superfluid density is about 10% of its clean value. Okay, and so that we consider this to be a pretty big success for using this disorder average theory or dirty D wave theory to describe a lot of the dome. It doesn't tell you, of course, about the very end of the transition, and I'll come back to that in a second. So yes, in fact, I'll come back to it now. So when I presented these results at some point, people from the ARPAS community said, well, okay, you've got disorder and perhaps some inhomogeneity that arises from disorder, but can you explain the fact that in these overdoped viscose samples, the gaps that one observes go considerably higher than the resistive TC, maybe as much as 30% higher. Okay, so these are data from this paper from, I think this is the Stanford group, for a 77 Kelvin sample. And the other thing is that whereas you would expect from a BCS type model that when the temperature gets close to the transition, the gap closes. Instead, what's seen in angular resolved photoemission, this has been seen for a long time, is that it fills. The density of states at zero energy rises, and eventually it looks like a normal state spectrum. So the question is, can you explain this with this mean field theory that I have been discussing? Well, the answer is partially. So we did a simulation, and the first thing that we found was that if we used ordinary Coulomb disorder, the degree of dispersion of the local gaps was not sufficient to explain the high temperature values of the gap, the very strong inhomogeneity of these samples. What we did, however, was something that goes back to another paper by Tamara Nunner and my group back in 2005, which showed that if you wanted to understand BISCO-STM data, you needed to assume that the pairing interaction itself was fluctuating on a scale of order 1 from site to site. That is to say, on a scale of the atomic, unit cell size, let's say. Okay, and only when we did that could we make sense of the STM correlations that were observed back then. So in this sense, we are able to, here's the picture reproduced. Can you guys see my cursor?
Yes.
Ming, can you see? Yeah, okay, thanks. Yeah, so this is the experimental data reproduced up here. And here's the result of the simulation. The TC is somewhere in the middle here. It's not well defined, so I don't draw a gray line, but it's somewhere around 0.15, 0.17, something like that. Oops, sorry. Um, and so this looks very similar to what's seen in the ARPAs. Um, on the other hand, if you look at the density of states, you don't see gap filling, you see gap closing. So that doesn't work. And so we turn to an explanation, which has actually been around also for quite a while, which is that phase fluctuations can fill in the gap. These are a lot of works from a lot of different people who worked primarily on homogeneous systems. And here we've combined those phase fluctuations in a time-dependent Ginzburg-Landau approach to with a disorder to show that the same thing happens. It's not particularly surprising. So the message is that if you would like to understand the physics of this transition, you need very strong variations in the local pairing interactions due to disorder, and you need phase fluctuations. Okay, I think that I've gone through already. Let me switch um, to the home scaling question. So we're coming back to the picture of Holmes's law, and I'm reminding you that this picture contains superconductors that are supposed to be D wave, mostly cuprates. I think all cuprates in this picture, and some which are supposed to be S wave. And they all lie on the same line, which is a pretty remarkable effect. If you think of this as being due in any sense to disorder, you immediately run into a problem, and that is that I told you, excuse me, I told you that the scaling, the Holmes scaling, comes out of a very simple picture of a dirty S-wave superconductor. But if you do the same calculation for dirty D-wave, close to where TC goes to zero, in other words, you find that the scaling is different. It should go like TC squared, not TC. So, open question. There are many explanations out there, but why do cuprates obey Holmes scaling at all, since we think that they're D-wave, and in some cases they are dirty? So we went back to the Holmes plot, and we put these calculations that I just showed you for the scaling of the superfluid density with the transition temperature due to disorder alone. Okay, and these are the Holmes variables, superfluid density versus sigma dc times Tc. And you see that the Holmes scaling line here, that's this gray bar, basically accounts for the data that were plotted here, with the exception of strontium ruthenate, which we added to the graph, which is way over here, has nothing to do with the Holmes scaling. Uh, but also there are no data points on our dirty D-wave curve. So what happened there? Um, And so we decided that a lot of this is David Bruin's insight, a lot of the dispersion of the data along this line comes from the fact that all of these samples have wildly different Drude weights. So it's interesting to try to scale out the Drude weights of both axes here. And what you get when you have that are when you do that, are two different scaling variables. This is called the superfluid fraction. It's the superfluid plasma frequency squared divided by the Drude weight squared, divided by, yeah. And then this is TC divided by the transport rate. So David and Steve went back through the literature, looked for all the optical data they could find, and they put as much data as they could on this plot with the new scaling variables. Initially, with the data that we have from the Holmes plot, and including strontium ruthenate, it still doesn't look very good, with the exception maybe that strontium ruthenate could be described as a weak coupling D wave. But now we don't still don't know what's going on. Now let's remember that cuprates are dominated near TC if they're near optimal doping by inelastic scattering. There's some kind of bosonic scattering, call it spin fluctuation scattering if you want, which dominates the scattering rate. Sorry, this keeps jumping back. And so we thought, let's see what happens if we try to model this. We did the simplest possible thing to model the inelastic scattering and put it back into the theory. So this is a model that goes back to Jules Carbot and Erwin Schachinger. It's just the Ellie-Ashburg equations, which you probably recognize for a D-wave superconductor. That's where the cosine 2 phi comes from. And some kind of ansatz for a strong scattering boson spectrum, which looks very generic. This could be an Einstein phonon. It could be a spin fluctuation, a very sharp one, anything. We plug it into the superfluid density, get the scattering rate from the optical conductivity, and we replot this, including the inelastic scattering. For three different assumptions about the inelastic scattering, weak coupling, moderate coupling, and strong coupling. And that just relates to how high the boson frequency assumed is compared to the size of the gap in the system. So what you see is that all the cuprates now cluster in exactly the same area, all the optimally doped ones, excuse me. The optimally doped cuprates are in this little dashed circle, which we call strong coupling D-wave. And because it's dominated by inelastic scattering, we've given it the questionable name of Planckian regime. This is the Planckian regime up here. On the other hand, David and Steve also found a lot of underdoped and overdoped data and plotted it for the first time on the same plot. And what you see is that this dirty D wave line is now being followed, but it ends in another set of points which is dominated by inelastic scattering. So we have let's see, we have the dirty S wave as well. I think that's all I have. I'm running out of time, so let me just go on to the end. Yeah, so you notice that the YBCO underdoped and the LSCO overdoped both fall on this dirty D wave line. So that's interesting. I don't want to suggest necessarily that the underdoped cuprates are Fermi liquids, but it's striking, I must say. Okay, so message here is that this is now a tool for classifying materials that gives immediate insight. This way of plotting things gives immediately insight into the disorder level, the order parameter symmetry, and the strength of coupling to bosonic fluctuations that are responsible for the superconducting pairing. So messages in the conclusions now. Dirty D wave works pretty well to explain these bulk properties. The home scaling, the new thing I showed you does not capture the unique physics of dirty D wave behavior. So we have this proposal of normalizing by the Drude weight, and then you see that there are four distinct scaling regimes: Planckian, dirty S, dirty D, and ultra clean. Why do underdoped and overdoped cuprates scale in the same way? I don't know. And then I just wanted to advertise at the end that there'll be an APS invited symposium that I helped organize on Monday at 12 o'clock, which is devoted to the question of what would cuprates look like if they were really clean. And some of this work will be presented there. This is Steve Kittleson, Bill Atkinson, David Broom, Bernard Keimer, and Emma Campillo. So thanks for your attention.
Thank you very much, Peter. The floor is open for questions for Peter.
I blow everybody away.
Yes, looks like you did. There's a question. Mohammed, go ahead.
Yeah, I'll ask the questions. You mentioned the low TC samples being a bit different. Could you comment a bit more on this? When you're showing the bosonic data, I think. Yeah.
Well, I think it's clear. Let's go back to the Bozovich data. I think it's clear that, yeah, so this is one sample that Yvonne measured and published in a separate paper in Journal of Low Temperature Physics, where it really does look linear all the way down to low temperatures. And that's something that doesn't come out of our theory. We really can't reproduce that. So I think it's clear that when TC gets close to the end of the dome, the superfluid density is getting very small in these samples. And so you're going to have phase fluctuations. And therefore, the disorder average theory that I'm presenting is going to break down. Where exactly that happens, I don't have a good feeling for, but I have a feeling it's that it's about this 10% level of the superfluid density. The same thing that I showed you is related to the inhomogeneity scale.
I see. Thank you. The other question I had, you mentioned the correlation being on the length scale of unit cell to produce some of the effects uh, of the disorder level that you see. Could you comment a bit more on how do you control this correlation length?
In the simulation, it's controlled by simply having a fluctuation of the BCS pairing potential with a Yukawa form and putting in a range. And so we studied ranges from unit cell size up to many times the coherence length. And basically, unit cell size up to nearly the coherence length gives you very similar results. Once you get uh, longer than that, obviously the response of the system is being averaged over the coherence length rather than the pairing fluctuation.
I see. All right. Thank you.
Yeah, sure.
Henry?
Hello.
Yes.
Henri,
Yeah,
salut.
how are you? I didn't understand finally whether you see a big difference between the thallium 2201 and the lanthanum strontium on the overdoped regime. Because the situation is clear that experimentally those two systems are very different.
Well, okay.
So how does that
I'll say a couple of things. So in the sense of they're being very different, I would say that the factor of 3 in the scattering rate you might consider to be very different, and it's clearly within my hypothesis, it's eliminating the quantum oscillations in the LSCO case. That may be sufficient to do so. On the other hand, the theory is essentially the same structure. So in that sense, they're similar. I'd like to mention that people have, to my great delight, started working on the thallium 2201 system again. There was a hiatus of about 15, 20 years where nobody made a sample anymore. And they've found techniques to make much better samples now. And I think that's going to change the game when they get published.
I agree very much with that. We have been fighting for long to try to synthesize these systems, and we never got them again. We have done one experiment, but
yeah, I gathered it's very, very difficult, not to mention toxic.
Okay. Well, I'll have to look in more detail to your paper, but I think it's interesting, this way of seeing the things. But that means you can include the disorder, and you could have a single explanation if you take into account correctly the disorder, if I understand.
That's the claim, yeah. I'd be happy to send you the papers, Henri, and I'd be delighted to get comments from you.
Okay, thank you very much.
Any other questions for Peter? If not, thank you, Peter, very much. Really appreciate your taking the time to
Thank you.
overlook cuprates.